Let R be a ring. Generally, it usually turns out we're mostly interested in commutative rings. Let little r be an element, and let little n be an positive integer. Then we're going to find little n times r to be repeated addition, r plus itself n times. And inductively, you could define it as n plus 1 times r is n times r plus r, with the base case that 1 times r is r, or recursively. So that makes this ... well defined. With that in mind, the definition of a characteristic is the following. The characteristic of a ring is the smallest integer n with the property that n times r is equal to 0 for all r and r. If no such n exists, then we say R has characteristic 0. The simplest example of characteristic of a ring is Z mod nz is equal to n. Why? Because here n times any element is adding every element to itself n times, and of course in a cyclic group of order n, every element has order divisible by n. I mean, a divisor of n. And so certainly then when you add it to itself n times, it's going to give you 0. I mean, in some sense, the characteristic, by the way, I'm also introducing char r to be a shorthand for the characteristic of the ring. You could define it to be the LCM of the additive orders. For every element in the ring. I mean, certainly that would make some sense because, well, assuming such a number exists, let's call it M, then certainly M times R is R plus itself M times. And certainly, if that's the LCM of the additive order of all the elements of R, then it's certainly a multiple of the additive order of this particular one. And so that's going to give you 0. Now, obviously, the issue here is, does it make sense to take the LCM of an infinite set, possibly infinite set of numbers? Well, that's where you get into the possibility that the characteristic isn't always well defined and why we have that option of 0. So there's usually two ways you can end up with 0 as a characteristic. One is if you get an element that has no finite additive order at all. The other one is if you have that the LCM itself is not well defined because you have infinitely many elements of distinct prime orders or something. Of course, one thing we point out very quickly is that if your ring has a unit, it turns out there's a much easier way to calculate the characteristic. It's the additive order of the unit. So if 1 has order n, then R has characteristic n. I put in parentheses that if 1 has order infinity, then that means characteristic 0. Proof, let R be an element in R in the ring. Then what's n times R? By definition, it's repeated addition. But you have a multiplicative identity, so you could replace R with 1 times R several times. You can factor out the common factor of R, and then you actually have 1 plus itself n times. But by definition of additive order, n times 1 is 0. And by properties of multiplication by 0, you get 0. So we see n times R is equal to 0 for every element in the ring. And we see no smaller number n is going to have this property because no smaller number n has this property for 1 itself. i.e. if you have m less than n, you'll find that m dot 1 is not 0 by definition of additive order. And so it's going to fail to be characteristic m because it fails the definition of characteristic for r equals 1. So therefore, r has characteristic n. On the other hand, if 1 has infinite order, then n dot 1 is never 0. And so that means there is no integer n for which n dot r equals 0 for every element of the ring, because there's no integer n for which you get the condition for 1. So r has characteristic 0. This bit is probably a little hard to follow because we have to remember the definition of characteristic here is that you found an integer n such that for every element in the ring. And so for a lot of these counterexamples, if I'm showing some n doesn't have that property, I just need to find some element in the ring where it doesn't work, and I'm taking 1 usually as that element. And to show that I have characteristic 0, what do I need to show? I need to show for every integer n there exists an r such that n dot r is not 0. And usually the easiest way is to pick the same r, which is what we did here. If your ring has an element of infinite additive order, then that's going to satisfy this condition. But there are other bad examples, but thankfully I'll never make you suffer with those ones, where that approach doesn't work and you actually have to pick a different r for each n. So there's some facts about characteristic. Now we get to the main one, which is that, so we already saw how you can compute the characteristic of a ring with a unit. Now we actually point out a nice fact if your ring is an integral domain. The characteristic actually has to be a prime number if it's non-zero. So it's either prime or it's 0. Note one thing that's kind of hidden in this proof. I'll actually spell it out afterwards. Because of the you have a unit. In that case, if it's characteristic 0, it means that the unit actually has infinite additive order. Alright, so let's suppose we're actually going to prove the contrapositive, sort of. So we'll let R be a ring of characteristic that's positive, and we're going to assume R is not prime. Then we're going to prove that R is not an integral domain. Now, of course, it could be the case that R has no 1. Well, then you're actually done. So we're going to assume that R actually has a unit. All right then, so our characteristic is not prime, so it factors as a times b, where a and b are natural numbers, and a and b are strictly between 1 and r. We're going to use a very sneaky trick here. We know that r dot 1 is equal to 0 by definition of characteristic, and r is a times b. So we're adding 1 to itself ab times here to get 0. I'm going to write it out in rows of 1s where there's a rows with b entries in each row. Now we're going to use the fact that 1 is a multiplicative identity to replace 1 with 1 times 1. And I'm going to factor out the common 1, black 1, in each row. And what do I end up with? A bunch of red 1s, about a of them added together, times the sum of a bunch of b 1s, b of them added together. And technically, it would have been nicer to separate this out by first factoring out the common black 1 in each row, and then now say, well, factor out this common sum of red ones out of each factor. But either way, you get this factorization, which turns into a times 1 times b times 1. It seems kind of weird to do it this way, but we have to remember a and b are integers. And so this proof seems kind of convoluted, but the reason why it has to be so convoluted is because a and b are integers. But it's worth pointing out a times 1 and b times 1 are actually elements in the ring. So we have two elements in the ring whose product is 0. More importantly, but by the definition of ring characteristic, we know that a times 1 can't be 0 and b times 1 can't be 0. Because that would imply, because remember, we have a unit, and so the characteristic of the ring is the additive order of the unit. And so if the ring's characteristic is R, the additive order 1 is also R. So we have two non-zero elements who multiply to give you 0. We've shown that R has 0 divisors. Therefore, it's not an integral domain. So if you have an integral domain, the characteristic must be prime. Of course, you have to wonder, it seems like such a strange way to prove such a result, but I mean, how do you show something is supposed to be prime directly? Well, that seems kind of hard. It's much easier to take the negation of a statement and assume something is composite because, well, that's a condition you can work with. And then you're just proving existence of a 0 divisor. And so that's what we did.